Okay. Hello.
Hi,
Hi, Dr. Nandini. How's it going?
very well.
Um,
Thank you for inviting me for
yeah,
this
sure. It's my
interview.
pleasure. And I always love to, especially talk to people that I did take courses with, did work with as well. So this would be a nice conversation that I was looking forward to. So this interview is mainly to try to like expand on your journey as as like a professor, and how did you get here, like talking through your undergrad, your grad, and like the professorship. Also talking about research and the choices you made in like deciding your research area and all of that. Hopefully to try to give like the students who are currently at OSU like a great like a holistic idea about like your work and your personality, and also get like give an idea for like prospective students who may be interested in working in condensed matter and like working with you, like who is Professor Nandini, what does she do, and all of that. So to start with, like the first, it's a lot of things. So we're gonna see how much we can cover out of it. So no pressure at all. We're just gonna work with the flow. I say. So the first thing is like if you can give us like a brief overview of your undergrad journey and why did you choose that school and major? So take
Well,
your time.
yeah, so very early on, I knew I liked science
Okay.
because this is like well before undergrad, like in school.
Like high
I
school or like
like
when?
even like middle school, I would say.
How did that start?
I love to do little experiments like mix oil and water and one thing sinks and something else floats. And it was just fascinating for me to see
See
this
that.
kind of thing.
Okay.
I also love biology,
Hmm.
like frogs, they would be hopping around, they would be croaking. And then in school, we would dissect these frogs.
Yeah.
And our school didn't provide frogs, we had to bring them from home.
Really?
So it started with that. But then I realized I kind of was a bit squeamish about cutting them. And also, I veered a little more toward physics and chemistry.
Okay.
Then, undergraduate, I went to Indian Institute of Technology in New Delhi. It's one of the premier institutes for engineering, but I wasn't interested in engineering. I wanted to do physics, but there weren't any institutes dedicated for science because
Okay.
I grew up in India, and most of the students, we had to pick our choices early on. So in school, we had to pick whether we want to do science or humanities.
Oh.
And then when we went to college, we had to pick engineering versus sciences. It was all very, or medicine. We had to make these choices kind of early on, unlike what I saw with my children in the US. So I was quite determined to do physics. So I went to Indian Institute of Technology where all the star students were going in for engineering, but I stuck on and continued with physics. And I'm very glad I did that.
So your major was like applied physics or
No,
like
it was pure physics.
it was pure physics?
Yeah,
Even though the school was engineering?
engineering. They had a physics stream.
Okay, that's really nice. So that's how you narrow it down to physics eventually.
Mm-hmm.
And then the next stage will be grad school. So
Yeah.
how did this
So,
start?
the thing is, it looks very linear,
Okay.
but as I think about it, my undergrad time was quite important for me because um, it was my very first semester at IIT Delhi. I got a C in physics and a C in math.
Oh my god.
And I was like devastated because this was the area I wanted to study. And here I am landing up with these grades. So, all the students coming there, it's, as I said, it's India's premier institute. They are all coming from the best students from everywhere. And, when pitted against the best, okay, I didn't perform well. Okay, moment of reckoning. So I go back that summer and I'm like, maybe I should rethink my career. But I just spent the summer trying to sort of unwind from that experience, and I came upon Feynman lectures. And they are so beautiful and so much narration that I just fell in love with that. And I was like, if this is physics, I really didn't know what physics was all about. High school was a lot about formulas and sticking numbers into formulas, but this opened a whole different world. So I decided, okay, now come what may, I will do physics. But I needed a strategy. So it was a very important time when faced with a failure. How do you strategize and how do you overcome it? And I came up with a very good strategy by talking to some professors who were understanding. So that was another very good thing. You have a challenge, how do you form some kind of a support group? Like mentorship. So I kind of came up with on my own with these kinds of requirements that I needed to flourish. And I ended up finally doing, really enjoying my time there. Nice. So now I come to grad school. That's why I talked about challenges, because it's never like one challenge. So I now come to grad school, and I went to Cornell, which was a really strong school. I wasn't sure at that time what kind of physics I wanted to do. I knew I loved quantum mechanics, and I also kind of liked statistical mechanics, these two things. So I went to Cornell and I tried to tell people I want to do quantum mechanics. And they said, no, there's nothing like that. You have to do either high energy physics or solid state physics. And I'm like, and they said they use quantum mechanics, but there's no feel like quantum mechanics. And I was like, oh, okay. So
there was no quantum information science.
No, you see, that's before all of this hype that we hear now, and now it's a real field. Yeah. And now that is kind of where my research has taken me.
That's amazing. But like, if we go a step back, like, why did you choose Cornell, or like, why did you choose to leave India to start with?
Yeah.
Like, did you apply to other places and this was the best choice?
Yeah,
or
I
like
applied to several places.
Okay.
And this was amongst the best offers I had. In fact, I even had, if I remember right, I had a fellowship, in fact, at Columbia. So I was trying to think I should go there. My boyfriend at that time, who's now my husband, Mohit Randeria, he had come here a year earlier to the US, and he was at Caltech. And he told me, for me, all of these, high energy physics or solid state physics, I didn't know much about these specific areas. But he said, go to Cornell. They have Ken Wilson, who may get a Nobel Prize one day, and it has many more options in terms of areas within physics. So since I was not decided, I thought, let me go there. Okay. And, of course, it's very far from Caltech, but for me at that time, the US was one dot. Just getting to the US was a big enough step.
Did you realize how separated
it
Cornell
was,
and Caltech are?
Yeah, that realization came only later.
Okay.
I did get into some schools near Caltech, but they were not as strong as Cornell. So that's how I ended up there.
Nice. Okay, so now, like, moving through Cornell, you decided to do solid state physics, I believe, then?
I did, and it took some time to come into, because I took a course, and solid state physics, when I got into physics, the charm was for me astrophysics. I loved that. The questions are big, the questions are important, like how did the universe begin?
The scales are
big. The scales are big, and you see it around you, you see the stars, so you want to know how it all began. The other field which is very powerful at that stage for me was because of Feynman and all these illuminaries. I wanted to go into high energy physics. That's the other thing. But when I took courses, I found there was a lot of detail in the courses. and they were mostly evaluating Feynman diagrams. That was not very inspiring. In condensed matter physics, I found, again, too many degrees of freedom when they would talk about anything. There were electrons, phonons, magnons, and I was like, what is going on? What are the big questions? That was not coming through. So that's when I found that it was useful to go to seminars and colloquia and hear about some recent results. And most of the times, I did not understand what people were talking about, but I could see their enthusiasm got to me. They were certainly enthusiastic about something. Yeah. Maybe I didn't understand it, but there was something in the field that was exciting. Yeah. So that was kind of how I went into condensed matter physics, because everybody, was talking about this discovery. One year they were discovering quasi-crystals. Every year of my graduate school, some new discovery happened. Okay. There was quasi-crystals, there was quantum Hall effect, fractional quantum Hall effect, super lattices. It was a very exciting field.
So you were excited by the disorder that was happening in the field? It's not a disorder, but it was like multiple things happening at the same time. Yeah. And just like, this is a question I would like to ask actually. Do you think that now there are big questions that the field is trying to answer, or it's still within the same state that you found that?
No, many things have been answered, and it has been absolutely amazing to see how, the growth of the field and how quantum matter has become so flourishing, and new concepts have entered it. When I was starting out, it was mostly trying to understand quasi, you have an interacting system, but you were trying to map it on to something weakly interacting, quasi-particles. So you could have electrons, they are strongly interacting, but you can effectively write them as weakly interacting quasi-particles. Or magnets had weakly interacting magnetic excitations, magnons, and so on. Now the focus has gone into things which are truly strongly interacting, and then they go into new phases of matter, superconductivity and different kinds of insulators, and also new concepts which were not important at that time. Symmetry has always been important in physics, but not topology. Okay. Topology was a field in mathematics, but it has been drawn into condensed matter in an integral way. Okay. First through quantum Hall effect, but now even more through all of these topology in graphene and multiple layers of graphene.
But at what point did you decide to do theory and not experiment? Or that was a decision you already had in mind from the start?
Yeah. I think I loved experimental puzzles. I loved experiments that brought up a puzzle. But I was really very keen on solving the puzzle. And so I think that is what drew me to theory. But I always kept connections with experiments. So one of the amazing things in Cornell, so the theorists were on the 5th floor, and the experimentalists were were in the basement, because that's where they can isolate their experiments from all the vibrations. But unlike today, where people leave the department and work from home, and they have multiple ways of working outside the department, we were always in the department. And so, we would take breaks from our work at it's midnight. What do? You take a walk to the basement, you talk to your friends, and you ask them questions about their experiments. So we had lots of feedback and lots of discussions with our friends, and we understood experiments in a very integral way. Cornell was very special there, that encouraged theory experiment dialogue.
And this affected you as a theorist
Yeah.
develop your like mindset and
Yeah.
like how.
So I've always liked to keep an eye out on experiments.
Yeah.
I like to do theory. I want theory to also be independent of the experiment, but to have some connection whenever possible. The best is when theory can make a prediction and, you know, somebody verifies it. That's really ecstatic.
That's amazing, yeah. All right, so back to Cornell, or like I guess now we're done with Cornell. If we talk about like the postgrad journey, you then applied for postdocs.
That's another challenge now.
Okay.
So, you know, my advisor was Neil Ashcroft, who you may know, he famous person. He wrote one of the tomes for solid state physics, Ashcroft and Mermin, that book. But I think he was also rather old fashioned. So, like later I realized I was his first woman student. So when I wanted to apply for a postdoc, I approached him and asked him if he would write me a letter. By then, my boyfriend, who was in Caltech, he transferred to Cornell. He and I got married. All that happened. So I went to him. I said, you know, could you write me a letter? And he said, oh, let me see. Maybe we can see where your husband gets a job, and then I could arrange a desk for you. And I was devastated. I was like, oh my God. The best part of it is, okay, I did not cry in his office. I managed to come out, but I was devastated because my first thought was, I have just been unsuccessful as a PhD student. I haven't achieved anything to the point that I'm going to get just a desk. I will have no appreciation in terms of any money for my position. So that was devastating. But again comes the question, what is the strategy? So, of course, there are two options. One is you can exit and do something else. But that is where the early setback was important. You see, Feynman lectures is now an integral part of me. Quantum mechanics, even more than Feynman lectures, the puzzle of the two-slit experiment, which drew me into physics, is not going away. So I wasn't about to leave physics. That I knew. So I'm like, okay, I have to stay in physics. Maybe my advisor doesn't think much of me. I didn't know at that time things like he's old-fashioned, hence he's prioritizing my family, you know. I was like, I need to save somehow my career. So the question was, what do I do? So I decided, also I'm very pig-headed. I was like, that's it. I've been hurt. I'm not taking a letter from my advisor. So that was an important but crazy decision not to take a letter. So the problem now was how to get a postdoc without my advisor's letter, how to convince someone to give me a postdoc. And luckily, there are scientists who will think independently and judge independently, and I did land a postdoc.
Okay. Were there like multiple positions you're choosing from? Or
no, at this point, my strategy was go to a big school that I'm excited about. So I went to Urbana-Champaign. They were hiring multiple postdocs, and they had a very strong condensed matter group. So I'm like, okay, go to a strong group that I really would like to go to and try to convince them to take me.
But so that was for the postdoc. You did the postdoc in Urbana-Champaign, and then you now ready to apply for the next challenge.
So I have to give a lot of credit to my postdoc advisor, David Sepperly, who made the bold move to take me on. I went there, gave a talk, and why I give him a lot of credit is my graduate work was all analytical. And I worked on multiple topics, among them disordered systems and mostly disordered systems and quantum size effects and things like that. When I was graduating, a fantastic discovery was made. That was high temperature superconductivity. And I was determined to work on that topic. It was a very important problem. To date, it is not fully solved. But what was important about it is, we have paradigms in physics, right? This is the paradigm by which we understand metals. This is how we understand insulators. This is how we understand superconductors. All these paradigms were broken by this one single discovery of high temperature superconductivity. So who would not want to work on it? Like a superconductor should at least emerge from a conductor. Then only you think it'll be superconducting at some low temperature. But here, this superconductor emerges from an insulator. Secondly, a superconductor, just very quickly, has pairs of electrons with opposite spin. So if you have a magnet should break the pairs. So usually, magnets are not superconductors. They live in different parts of the periodic table, and even material-wise, which are composites. Magnets are not usually superconductors, but high-temperature superconductors that were discovered in 1987 when I graduated were exactly born from an insulator and a magnetic insulator. So it's breaking all these paradigms. I had to work on that topic. So I went to Urbana and I was talking to David separately, and I said, this is the problem I want to work on. And, now it's a very wrong way for someone to convince someone to hire you. Usually you have to work on a problem of their choice. But that's where I would say he was open-minded about hiring me to work on that topic. And secondly, I had done my entire thesis using analytical methods. I'd not used any computers. Now this problem, the one I wanted to work on, was arising because of strong repulsion between electrons. So it's a many-body, strongly correlated problem. No quasi-particle picture is going to describe this. And to me, it seemed at that point, hearing about the ingredients of the problem that Phil Anderson laid out very early on, he basically identified the key ingredients, which was strong correlations. I was like, a computer should be able to handle that, because strong correlation is basically a statement that if you have an electron of spin up, a spin up electron at the same site is not possible because of Pauli exclusion principle, but spin down is allowed unless there are strong correlations or strong interactions. So analytically, it turns out this constraint is very hard to put in. But numerically, it looks like just tell the computer, if there is an electron at this site with spin up, don't put a down electron there. It just is a one-line state if condition in a code. So I was like, I even know in my mind's eye what I should be doing, but I have never programmed. But David separately was like, okay, I will work with you on this problem. So I was quite thrilled.
So you did all the numerical work in your postdoc?
Yes.
In Illinois?
Yes.
Wow.
And so that was an exhilarating journey. I worked super hard, like morning till the wee hours of, from early morning I would start, take very short breaks for food, sleep very little, that kind of a journey. But I was dedicated to work, as hard as possible, because I had gotten this opportunity to work on a problem I really cared about, much more than the problems in my graduate work, which somebody else was giving me a problem. That was, I think, a very key factor. It was a problem I really cared about. And I was learning the tools, and just the atmosphere was like electric in the community. So it was really exciting to be part of that. And I was just grateful to get this postdoc in such an exciting place.
That's an amazing story to hear. did this bring a new challenge for you when you applied for assistant professor? Or like, was there a challenge actually in this transition?
Yes. So, now my husband and I, we had to make sure we got positions together. Luckily, Urbana, we did get positions together. So, it was quite amazing. I got a position without my advisor's letter. He, of course, got a wonderful position with Tony Leggett. And we had a very productive time in Urbana. And the challenges were then to find faculty positions together. And that was little complicated. So my husband, Mohit, got a faculty position right after Urbana. He became a faculty at State University of New York in Stony Brook. So he became an assistant professor there. And I was still not quite ready for an assistant professorship because I'd kind of changed techniques. So I wanted to do one more postdoc. So I got multiple postdoc positions, but I took the one at Stony Brook. And now I would say that is a strategic mistake, because if you are trying to find a faculty, at least in those times, the community was not so supportive of hiring partners. So they viewed that against me, that I had done a postdoc there, and they didn't want to hire me as a faculty. So hence I didn't want to just take up anything nearby, because somehow, when people know you want a job, they are less willing to give you a job. So I decided to apply widely, and I got a scientist position at Argonne National Lab.
Okay.
So that's how I moved to the Chicago area.
All right. But then how did OSU come to the picture?
Okay. Again, it's never been a very straight journey, but okay, I'll tell you quickly, just so you can dwell on whichever part of it you want. From Argonne, so Mohit also transferred. He was generous and decided to give up his assistant professor position, which was a wonderful place to be, but he gave that up to also come to Argonne so we could be together. And we were there for about 5 years. And then surprisingly, we got these joint offers from India, from Tata Institute of Fundamental Research in Bombay, which is India's premier institute. So we ended up making a transition back to India, thinking this was going to be like a permanent move. By then we had 2 children, who were born in the US, and we sold our house, packed up everything, went back, and we were there for about 10 years. Fantastic time, had a very productive time there, fantastic colleagues, really good students that we worked with. But then somehow it seemed like it was a good time to come back to the US. So we applied, and again we had a couple of options, and then decided to take Ohio State, where they offered both of us positions this time. Okay. So it was a very good place to join. So it's a long journey, yes.
That's a long journey.
But I think at each time, when you're young, you're very hopeful, and there's stress. There is stress, but there's also kind of a bounciness with the stress, because you can't see too much into the future, and that's what I think I realized. Both of us, Mohit and I, look just in front of ourselves. We are not big planners. So it taught us a little bit about ourselves. We take what is in front of us and try to enjoy that time, rather than worrying about too many things, or you can't control that. So I think on the whole, it has been a pretty exciting journey.
That's a really exciting journey. Thanks for sharing that.